Good afternoon. I am presenting Raman spectroscopic analysis of dialysate in patients with acute kidney injury undergoing hemodialysis. Acute kidney injury, severe enough to require dialysis support, has a mortality rate up to 40%. The duration of hemodialysis treatment is generally prescribed for patients with acute kidney injury without attention to any particular kinetic modeling strategy. The possibility that suboptimal dosing of dialysis may contribute to the high mortality rate of acute kidney injury led us to determine whether spectral analysis of the products of dialysis might allow for more rational timing of the procedure. We performed a study of 4 patients with acute kidney injury who prescribed hemodialysis as a part of their medical management. Our study protocol is shown in Figure 1. Hemodialysis is the process during which uremic toxin in the blood get filtered across a membrane into pure dialysate. That is then discarded as a waste dialysate. We obtained samples of pure dialysate prior to the initiation of dialysis, followed by collection of waste dialysate at 30 minutes interval throughout each treatment. We subjected these samples into Raman spectroscopic analysis to determine their molecular constituents. Figure 2 reveals a typical Raman spectral pattern for urea and for creatinine, obtained from reference library of molecular standards. Using these standards, one can establish the type and concentration of individual substance in dialysate. We were interested to determine whether the molecular profile of waste dialysate collected from our acute kidney injury patient would be similar amongst our patients. This question is addressed in next to figure. In this conical plot, the Raman profile for each sample of waste dialysate is represented by a single dot that migrates to a specific location. As you can see here, the molecular structure of waste dialysate congregated together in 2 patients, suggesting similar biochemical profile, but differ in other 2 patients. Figure 4 shows the individual molecular component involved in constructing the above plot. These data reveal potential variability amongst patients in the products of uremia that are removed by hemodialysis. Figure 5 shows the change in the molecular structure of waste dialysate over time. Pure dialysate sampled at 0 time clusters on the right side shown as red dot. 30-minute interval sampling of waste dialysate shows progressive dislocation of clusters of the dots in this conical plot, indicating changes in the molecular composition over time. Subsequent analysis revealed an initial steep decline in the concentration of molecular constituents in the waste dialysate, followed by lesser decline suggesting eventual equilibration. Unfortunately, the migration of these molecular clusters was limited by the rather short duration of dialysis treatment in this sample of patients. We conclude that Raman spectroscopy can be used to analyze molecular components in waste dialysate, monitor their decline until they reach equilibrium. Also, we conclude that the molecular composition of waste dialysis differ amongst patients with acute kidney injury, as well as from treatment to treatment in the same patient, suggesting the need for customization of dialysis. Finally, this spectral technique can be run rapidly and inexpensively at the bedside in real time, allowing for immediate adjustment of dialysis time. Thank you so much.